equations and symmetric equations on planes and lines. And we finish up this question, finding the intersection of two lines. So now we're going to go a little bit step further. So the interesting point is two planes are parallel if their normal vectors are parallel, meaning that each is a scalar multiple of the other. If they're not parallel, then their intersection so they intersect on a straight line, and the parallel vector is the cross product of the normal vectors. Okay. And that actually leads up to our next example. So find the symmetric equations for the line of intersection L of the two planes x plus y plus z equals 1, and then x minus 2y plus 3z equals 1. So what's happening here is I have two planes. Let's say this is plane 1. That represents this one. And then plane 2 does something like this. Where the line that intersects it is right here. Okay. So we want to see when these two like pieces of papers cross each other itself, right? So it goes right through it. One paper goes right through the other. Now, this is an interesting type of question because you can actually pick a point in perspective wise. So remember, we have 3 different variables. So that means 2 of them can be independent and 1 of them is forced. And we can actually pick which ones will be independent and forced. So what I mean by independent and forced is, well, notice they're fixed, right? X, Y, Z the addition of X, Y, Z must equal 1. And this has to satisfy the same situations here, right? That single point, there's a single point on here where it does actually cross, kind of like what we did up there. So instead of plugging all of this in and make it a little more difficult itself, we can kind of pick a point that's very similar to it. And we're going to pick the point X, Y, 0. Because it does satisfy the other two. Because if Z equals 0, then we get X plus Y equals 1. And X minus 2Y equals 1. So it does satisfy it, right? And it makes it much easier to deal with now. Okay. So now we want to find the point of intersection of these two lines now. And this is just solving for a system of equations now. So let's say we want to get rid of X, for instance. So let's say we do X plus Y equals 1, multiplied by -1. We get that. Crossing this out, we get 3y is equal to 0, which doesn't make sense, right? Oh, y equals 0 then, right? So therefore, we plug it back into any of these, we find out that x equals 1. So the point of intersection, so the exact point where these two planes intersect is the point 1, 0, 0. This is the point of intersection. All right, so now that we have a point, how do we find the system of equations? Basically is same thing as finding the parametric equations, right? Given a point, we also need a vector that's parallel to this line, and that is what we just talked about earlier. If the planes are not parallel, therefore they intersect on a line, which is what we're trying to find. We got the point that's on the line, and the parallel vector is the cross product of the normal vectors. So now all we have to do is find the cross product, and that gives us our normal vector of this line. And this goes back to the last linear equation plane, is if we're given a plane equation, a line in planar portion in this way, our normal vector is the values of a, b, c in front of the variables themselves. So if we do this twice down here, we'll call this vector v, is going to be, oops, it's going to be the vector 1, 1, 1. If I do the same thing over here, let's say vector u, this is going to be the vector 1, -2, 3. And just for, sake, even though, maybe this could be wrong, we're technically correct because notice this does not follow the first one, right? They're not parallel to each other because their normal vectors are not scalar multiples of each other, meaning, right, one is not a multiple of the other. So there's no way that happens. So they do actually have an intersection. So this actually did work here, right? All that fun stuff. Yeah, so because we know these intersect, right? And again, think of like x, y. X is the independent variable, y is the dependent variable. But we're in 3 dimensions, so therefore, 2 of them could be whatever I want it to, and the third one has to be independent variable. And the cool thing is you could choose which one you want to be the independent variable. So I chose z to be one of our independent. I should pick anything I wanted to. So I just made 0 easier to make it break it down itself. Which if since we need a system of equations and there's no way I don't want to solve for one variable, plug it into the other one and have that horrible menace, you could set one of them as long as it satisfies this condition, right? And it did actually satisfy because this point does actually satisfy those two. Okay, so like I could put 0 for x and it would have been the same thing. Pretty interesting. Okay, so now that we have our 2 vectors, let's find the cross product. So the cross product of vector v and u. So this is going to give us 1, -2, 1, 3i minus 1, 1, 1, 3 j, and then 1, 1, 1, -2 k. Okay, so this is going to give me 3 plus 2 is 5. 3 minus 1 is 2. And then finally, -2 minus 1 is -3. So there's my vector. And now finally, we put it in our symmetric equations. So remember, symmetric equations are the fraction format. So it's going to be the point divided by our vector. So the first one is going to be x minus 1 over 5 must equal y minus 0 over -2, and then z minus 0 over -3. And there is our symmetric equations for the line that is Ross's, or the intersection line. Any questions there at all? Okay. Right. So that's the case. We'll finish up the section with distances. So how do we find the distance between plane and a point on anywhere we want? So let's suppose we're given a plane. And we want the distance between this point and the plane. Well, remember, distance is always going to be perpendicular. So I'm just going to make this down. So this point here. So this is going to be our distance. This is what we're going to be looking for, D. Now, because we have a plane, right? Remember, a plane can be represented as two different things. A point on this plane, we'll call this P naught here, and a vector that's parallel to it. So joining these two. And the key thing is, remember, to find a, what's it called? We need a normal vector. Well, isn't that interesting? That this point P can be its normal vector. Now, the only thing we have to know is because we have a point here, we have an angle theta that crosses it. So to find this distance, all this really is, it's a scalar projection. So if you guys remember, scalar projections was the components of A to B, which equaled the normal vector times B over the normal vector. So if I do the length of this now, of the scalar projection, that actually gives us our distance. And broken all that funds down gives us exactly that. So the distance between any point and to a plane is given by the equation, which is basically the projection of B onto A, or the length, sorry, of the length of the projection of the B onto A. Where again, the key thing is N, or this plane, has to be a normal vector. So again, we still got to find that normal vector of these planes. So let's try to put this to practice now. All right, so find the distance of each. So first one's going to be pretty straightforward right from the definition. Next one's going to be a little difficult. We got to go around some stuff. All right, so if we want to find the distance between the point, which we're given, and the plane there. So straight off what the definition represents, right? So x1, y1, z1 is the point itself, and the plane is, here's my A, B, and C in my normal vector. So now plugging everything in, the distance between that point and the plane is going to be the absolute, or the length of A times x, so 3 times 2 plus -4 times 0 plus -1 times -1 all over the square root of the normal vector, right? The length of the normal vector. So 3 squared -4, -4 squared plus -1 squared. This is going to be 9, 16, and 1. So that gives me 26. And the top, we get 6 plus 0 plus 1. Oh, almost forgot the D. D was there. So there. So 6 plus 1 plus 8 is 8 over the square root of 26. And then since this distance can never be negative, that's why the absolute value basically is the same thing there, because the length will always make it positive. So like I said, this is straight off the definition. So just like everything else in math, especially for this class, what if you're not just strictly doing straight off the definition? So find the distance between the parallel lines. Okay, so now we have two parallel lines, or sorry, not a line, parallel planes, sorry. these two are parallel. We want to find any point on this one and this distance right there. So we're looking for that distance there. Okay, so just like the last one, we can kind of choose how we want to do stuff, right? Now, remember, because they're two parallel lines, their normal vectors are going to be the same. Okay? That's a key component. And hopefully their normal vectors are the same or are a scalar multiple, right? Let's look at this right here. So this vector here is 10, 2, and -2. And this normal vector for the other one is 5, 1, and -1. And notice they actually are parallel, right? This is a scalar multiple of 2. So if I multiply this everything by 2, I get exactly that back. So check. These are actually parallel to each other. So if you're wondering how on the other example you would know the two vectors are parallel so they never cross, it's exactly just check it. Which means our intersection point doesn't even make any sense. Okay, so we want to find the distance between this point. So the problem is we need to find an initial point. Okay, so in other words, a point on, let's say, plane 1. Okay. And it really doesn't matter which one you use, to be plane 1. I'll use this one for instance, just for since it's the first one given to me. So we want to find a point on this plane. Any point, and that's a key thing, right? Since they're parallel, it doesn't matter if I choose this point, that point, that point. It's an arbitrary point on the actual plane. Okay, so just like last time, I'm going to choose the easiest of these two. Now, if you're wondering what do you mean by the easiest of these two, just like I said last time, right? I have two independent variables and one dependent variable, and I get to choose the two independent variables. So I'm going to force x to be 0 and y to be 0. So I want to find the point 0, 0, z on this plane. And again, right, it doesn't matter what point I choose because the distance is always going to be the same. So now if I plug both 0, 0 into this equation, I just get 2z is equal to 5. And I just solve for z. So z is equal to -5 halves. So my initial point P naught on this plane is going to be 0, 0, -5 halves. Okay, so now that I have a point, according to my definition, I must also have the vector of the plane, which is fine because I could, we already have the vector of plane. We already checked it that they are parallel to each other. So again, since they're scalar multiples, I'll just use the smaller of the two. So now we have a point and a vector that's on the plane. So now I could just find itself, so distance itself. So the distance is now going to be 0 times 5, which is going to be 0, plus 0 times 2, which is also 0, plus -5 halves times -1, all over the magnitude or the length of the vector, right? So that's going to be 5 squared plus 1 squared plus 1 squared. So this gives me 5 halves on top over the square root of 20, 5, 6, 7, 7. Oh, yeah, thank you. Thank you for that. So d goes over -1. Thank you for that. So d goes over to -1. Ooh. What does that give me? This is 2 over 2. So 3/3. Thank you. Forget about you.